You ever feel like you're tackling a really naughty problem, maybe something scientific, or even just, how to rearrange furniture?
Yeah.
And you just wear those spatial, those logical connections would just click faster.
Oh, definitely. It's that feeling of wanting to just get the structure underneath.
Exactly. Without getting totally bogged down.
Well, that feeling is kind of what we're exploring today. We're diving deep into some really fascinating research. It looks at a pretty novel way to sharpen spatial and logical reasoning in teenagers.
And it sounds like it's about as far from a stuffy classroom as you can get.
That's putting it mildly. We're talking about Lost in Space, this research project that's a mix of an alternate reality game, a classic board game feel, and augmented reality tech.
Wow. Okay, so like a supercharged game. Designed to boost critical thinking, but actually be fun.
That's the idea.
Yeah.
And our mission here for this deep dive is basically to unpack how Lost in Space was built, what the early findings suggest about, whether it worked, and what the students actually thought about it.
And we're basing this all on an academic paper that documented the whole thing.
Correct. Straight from the source research.
Okay, let's jump in. Why these specific skills, spatial ability SA and logical ability LA, why are they such a big deal?
Well, they're really seen as foundational, especially in STEAM fields: science, tech, engineering, art, math.
Right, STEAM. Makes sense.
And the research points out that SA spatial ability is tied directly to how well we handle visual information, remembering it, turning it around in our minds.
Like an architect visualizing a building from blueprints.
Exactly that. Or an engineer designing a component. That's SA.
Got it. So it's more than just seeing, it's mentally doing stuff with what you see. And LA, logical ability, that sounds more like step-by-step thinking.
Precisely. The paper frames LA as the core of computational thinking. Programming, sure, but broader too.
Broader how?
It's about using those core computer science ideas, algorithms, patterns, abstraction to tackle problems, any problems really. Designing systems, understanding complex information, even human behavior in a way.
Okay, so really fundamental skills. But if they're so important, what was the gap? What were these researchers trying to fix?
That's a key point. There's lots of focus on teaching computational thinking through coding, right?
Yeah, seems like everyone's learning to code.
But the research highlights a gap. There aren't many studies looking at activities that build both SA and LA together, especially in realistic settings. And there's this challenge of taking computational thinking skills from coding and applying them to real-world problems that aren't about programming. Think urban planning or figuring out transport logistics. Those need both spatial and logical skills.
Okay. So you might be a whiz at Python, but struggle to mentally map out how a new bus route actually sits into the city grid.
Exactly. And that's where situated learning comes in, learning in context. The researchers believe that putting learners in engaging situations, really grabbing their motivation, is key for improving both SA and LA.
So make the problem real, or at least feel real.
Right. And games are a great way to do that. Turn those real-world problems into, game tasks that can boost motivation and help cultivate these skills.
Okay, that sets the stage nicely. So,
Yeah.
Lost in Space. Tell me more about the game itself. What's the actual concept?
Well, the really interesting thing is how it weaves together three strands. You've got alternate reality games, or ARGs.
Oh, right.
You've got the face-to-face interaction of board games.
Right.
And then you add the visual kick of augmented reality, AR. And it's all underpinned by this idea of multidimensional scaffolding.
Multi-dimensional scaffolding. Sounds complex, but important. Let's break that down. What does the ARG part bring to the table?
ARGs are all about immersion. They pull learners into scenarios that feel real, encouraging exploration within that context, kind of blurs the line, makes the learning feel more immediate.
Got it. So the environment itself is part of the puzzle, not just pieces on a board. What about the board game element then? Why include that?
That's crucial for the social side. Face-to-face teamwork, discussion, collaboration. It provides that shared physical space that, purely digital stuff can sometimes miss.
Yeah, that makes sense. You're actually there talking, pointing at things.
Yeah.
And then the AR piece, that sounds like the high-tech magic. How does that work?
The AR provides what they call representational multimedia cognitive scaffolding. Bit of a mouthful, I know. But think of it like this. Instead of just seeing a 2D picture of a 3D shape, the AR can overlay a virtual 3D model onto, say, a physical card.
Oh, cool. So you can see it from different angles.
Exactly. Rotate it, examine it. It gives much richer spatial information. It's a kind of cognitive scaffold, direct support for understanding.
Okay, so you scan something real, get a digital layer with more info. How does this tie into that multidimensional scaffolding idea again?
Right. The AR app is sort of the brain. When players scan the game cards, it talks to a database and gives instant feedback. This feedback is designed as scaffolding cognitive scaffolding, helping them understand, and metacognitive scaffolding, helping them think about how they're thinking.
Layers of help, basically.
That's a good way to put it. Guiding their SA and LA thinking.
Okay, I'm starting to get the picture. It's this blend of real-world interaction, solving a tangible problem, but with digital guidance popping up. So what are the students actually doing? What are the pieces, the gameplay?
Okay, the physical bits. You've got posters around the room showing spatial and logical concepts. Then there are these irregular blocks, physical clues.
Okay, physical objects.
Then perspective cards. These are key. The AR app scans them to show those 3D views we talked about. And finally, small building blocks like actual little bricks players can use to physically build stuff.
Right, so info, clues, interactive cards, and building bits. How does a game session work?
So you have 2 to 8 students split into 2 teams, Team Yellow and Team Red in the study. They've got 40 minutes, the components are set up in a room, and each team has a mobile device with the app.
And there's a story.
Yeah, a bit of an escape room vibe. They're supposedly going to a poster exhibition, but whoosh! They get pulled into this empty exhibition center.
Trapped.
And the only way out is to figure out the puzzles scattered around using the models, posters, and clues.
Okay, fun premise. What's the main goal?
Solve 4 puzzles in 40 minutes. Each puzzle is like Model A plus Model B. They need to find the physical models for A and B, then use the AR app to do a logical deduction to figure out which model is the answer.
So physical search, then virtual logic. How do turns work? What can they actually do on their turn?
It's turn-based. They choose one of 3 actions using the app. Action 1, build a virtual 3D model.
How?
Scan 2 perspective cards showing different views of the same model. If it matches, boom, a rotatable 3D model appears on screen. That's a big cognitive scaffold for spatial understanding.
Yeah, I can see how that would help massively. Okay, action 2.
Action 2, search for hints. They use the device camera, scan the room for 30 seconds looking for hidden posters.
Like a treasure hunt element.
Kind of. Successfully scanning a poster unlocks the logic operation function in the app. Then, the app can animate how a logic operation works using 2 scanned cards.
So finding posters gives them the logic tools. Clever link between exploring and problem solving. And the third, action.
Action 3, solve a puzzle. They scan 2 perspective cards they think show the same model from different views, and that model is the answer to the current puzzle. Get it right, they score points, move to the next puzzle.
Okay, so it's this cycle. Find clues, build virtual models, unlock logic tools, try to solve. And what about working together? What interactions are allowed?
Oh yeah, that's encouraged. Discussion within the team, definitely. Physically playing with those little blocks to figure things out, and even watching what the other team is doing.
Observing the competition. Interesting.
Yeah, that peer interaction is meant to be part of the learning process.
Okay, that game sounds intricate but really engaging. Now let's dig back into that multi-dimensional scaffolding. We've mentioned cognitive and metacognitive. Can you break down the specific supports built into the game?
Sure. So scaffolding is just about those supports that guide learning, right? Lost in Space uses 8 specific mechanisms grouped into 3 types: cognitive, metacognitive, and peer scaffolding.
Let's start with cognitive. Direct help with understanding.
Exactly. The first one, C1, is those posters we mentioned. They have info on logical problem-solving graphs, text right there in the room for reference.
Like cheat sheets, but integrated. What's C2?
C2 is subtle. There's a little kitten head printed on the perspective card.
A kitten head.
Yeah. And the way it's pointing indicates the orientation between the 2D card image and the 3D model it represents. A nonverbal spatial cue.
Clever. Okay, C3.
C3 is that scan the hints to get the logic operation function we just talked about. Finding posters unlocks that AR animation to check their logic.
Got it. And C4, the last cognitive one.
C4 is simple. English letters printed on the bottom of the physical models. These letters are direct hints linking the models to specific puzzle questions.
Okay, so those are all about providing direct information or cues.
Yeah.
What about metacognitive scaffolding? Helping them think about their own thinking.
Right, helping them strategize and reflect. M1 is the small building bricks themselves.
The physical ones.
Yeah.
How are they metacognitive?
By letting students freely build and test ideas physically. It externalizes their thinking, lets them self-monitor their reasoning, and helps them communicate ideas to teammates. It's hands-on exploration.
Makes sense. Physically trying it out helps you understand if your idea works. What's M2?
M2 is building the virtual 3D models in the AR app. Constructing those from the 2D cards helps them visualize and reflect on that 3D to 2D relationship. Rotating the virtual model aids spatial reasoning.
Yeah, being able to manipulate it virtually seems huge. And M3?
M3 is simply that info about solved puzzles stays visible in the answer area. Teams can look back, see what worked, reflect on past strategies, and maybe adjust their approach for the next puzzle.
Learning from their own progress in the game. Okay, finally, peer scaffolding. Since it's team-based, how does that work?
This leverages the interaction between players. The main one here, P1, is simply allowing teams to observe each other's actions.
Just watching the other team.
Yeah, watching the opponents can spark ideas, reveal strategies, maybe even show where a hint is hidden that your team missed. It fuels discussion and collaboration within your own team.
Learning by observation, even from rivals. So, Lost in Space sounds absolutely packed with these different support layers. The big question then, did it work? What did the actual research study find out?
Okay, so the researchers ran a quasi-experimental study. It's like an experiment, but maybe without perfect random assignment. Pretty common in real-world school settings. They had 127 10th graders. One group played Lost in Space, experimental. The other used traditional materials on the same topics, control.
And they tested them before and after.
Yep, pre-test and post-test for learning achievement.
And the results? Did the game group learn more?
Well, it's interesting. The experimental group, the game players, showed a significant improvement in their scores from pre-test to post-test.
That sounds good.
It is, but the control group didn't show that same significant jump. So the game definitely seemed to catalyze learning within that group.
Okay, but I think the paper mentioned something else about the comparison between the groups.
Right. When they compared the final post-test scores between the two groups and statistically controlled for where they started on the pre-test, there wasn't a significant difference between the game group and the control group overall.
How do we square that?
Oh.
The game helped them improve, but they didn't end up significantly ahead of the others.
It suggests that while the game was a really effective way for that group to learn and improve, the final level of understanding reach wasn't massively different from the traditional method when accounting for starting points. But, crucially, the game did produce those learning gains. It supports the idea ARGs can teach effectively.
And the scaffolding probably helped apply the knowledge within the game.
That's what the researchers suggest, yeah. The multidimensional scaffolding likely played a big role in helping them actually use the concepts during play.
Okay, so the game spurred learning. What about the experience itself? You mentioned flow state earlier. What's that, and how did the students feel playing?
Flow state is that feeling of being totally absorbed, right? Losing track of time, fully focused, challenge matching skill, deep engagement.
Right, getting in the zone.
Exactly. They used a questionnaire and found the overall flow state for the game players was significantly higher than the midpoint. They were genuinely immersed.
That's great. Were any parts of flow particularly strong?
Yes, time distortion, feeling time fly by and concentration scored highest. They were really focused and lost in the game.
Ideal for learning. Any aspects less strong?
Interestingly, action awareness merging was lower.
What does that mean?
It's that feeling where your actions and awareness are perfectly seamless. The researchers think maybe because the game involved exploration before finding solutions, there might have been moments of slight confusion, like, what do I do now? Yeah. That could break that perfect seamlessness.
Oh.
And the overall flow wasn't like off the charts deep. It suggests that designing these AR educational games needs careful balance, keeping players engaged without overloading them cognitively. Maybe a bit more guidance initially within each puzzle could help.
Good point, the balancing act. Now, what about the scaffolding? Did the kids even notice all these support systems? Did they find them useful?
Crucial question. And yes, mostly. They found students were aware of most scaffolding mechanisms. Perception ratios were generally over 50%.
That's good. Which one stood out?
Metacognitive scaffolding did well. The small bricks for building M1 and the virtual 3D models in AR M2 had really high perception rates. Students noticed them.
So the hands-on and the cool virtual stuff were definitely perceived. Any that were missed?
The least perceived was C3. Scan the hints to get the logic operation function. Probably because accessing it was less obvious, maybe less intuitive in the design. But it wasn't essential to finish the game.
Okay, so they generally saw the supports. But usefulness. Did they actually help?
Yes, feedback on usefulness was mostly positive. Students felt the scaffold helped them focus and think better.
Any specifics?
Yeah, the posters C1 and the letters on the model C4 were rated highly useful direct knowledge, right? The virtual 3D models, M2, were seen as great for spatial visualization. The small bricks, M1, were valued for helping team discussion. And even observing competitors, P1, was seen as useful for improving team strategy and talk.
Interesting. So different scaffolds helped in different ways, some with info, some visualization, some collaboration.
Exactly. And a key finding was that any scaffolding that encouraged peer discussion, regardless of type, seemed particularly beneficial.
Makes sense. Learning together. So, wrapping this all up, what are the main conclusions from this deep dive into Lost in Space?
The big takeaway is that this blended approach, ARG, board game, AR, plus multidimensional scaffolding, looks like a really beneficial framework for learning tricky things like spatial and logical abilities.
Shows promise.
Definitely. The Lost in Space game itself led to significant learning gains within the group that played it, and they had a positive, engaging experience. They were in flow.
And the scaffolding wasn't just decoration, it actually helped.
Right. Students were aware of most of it, found it useful, and it supported their essay and LA development through that active exploration the game encouraged. The whole multidimensional scaffolding idea seems solid.
Okay, so let's summarize our deep dive. We've seen how Lost in Space mixes AR, board games, and smart learning supports to make complex topics engaging and actually effective. The research really suggests that active exploration in an immersive setting with these different kinds of help leads to real learning and focus.
Yeah, and for me, the real aha moment is seeing that learning improvement after playing. It wasn't just a fun diversion, it was a genuine learning tool. And seeing how different scaffolds helped in specific ways, direct info, visualization, teamwork, highlights how crucial thoughtful design is.
It really makes you wonder, doesn't it? How could these ideas, multidimensional scaffolding, immersive game learning, be used elsewhere? Other tough subjects, professional training.
Could AR-enhanced games become a mainstream way to learn complex stuff quickly and deeply?
And what were the absolute key ingredients in Lost in Space that made that aha moment happen for the students? Was it the AR, the teamwork, the story?
Good questions. For anyone listening who's intrigued by this mix of gaming, AR, and education, definitely look up the original paper. It goes into way more detail on the methods and findings.
And maybe just think about your own learning experiences, right? What made things stick for you? Could some of the ideas from Lost in Space be part of the answer?
Absolutely. Food for thought.
Definitely something to mull over. Well, thanks for joining me on this exploration of Lost in Space. Until our next deep dive, keep those mental gears turning.